Capacitors and capacitance. What we're going to be looking at in this presentation is an introduction to capacitors and their operation within a DC circuit. Capacitors are a device that will store electrostatic charge. So a little bit different than an inductor. A capacitor is something that is storing, you could almost think of it as a static shock. When you scuff your feet along the carpet and you get a shock from something, that static charge is what a capacitor is actually capable of storing. They accomplish this by separating two plates with a insulating dielectric. So dielectric meaning something that is insulated or insulating from current movement. And so the dielectric is in between the two plates, and with that separation of those two plates by the dielectric, you end up with a buildup of charge on one side or one plate versus the other. Capacitance is affected by the following variables or construction considerations. So capacitance C is equal to EA over DI. The first thing is the distance between the plates. Capacitance is affected inversely by the distance. More distance means less capacitance. The second item is the dielectric strength of the material between those two plates. A higher strength of dielectric means that it can handle a higher charge. And finally, the surface area of the plates. How large are the plates? A larger surface area will render a higher capacitance value. So this just shows visually the difference between. There, the area of the plates is smaller, so there's less capacitance. This one, the distance between the plates is very small, so there's more capacitance. And this one has a different dielectric compared to air. And this one will again have more capacitance. Capacitance itself is measured in farads. It's a physical property made up of those three different construction requirements. The symbol we use to represent capacitance in equations is the C. And typically a capacitor is sized in a measured value in the microfarad realm. So typically microfarads is what we're looking at. Very small values. It's highly unusual to get large capacitors, especially something like 15 or 25 or 400 farad is almost unheard of. This down here is more the norm of what we would expect to see within the electrical industry. This is 600 microfarad. Micro is a script of U, farad, F, and if you were to convert that to farads, it's 0.0006. Because micro represents a decimal place movement of 6 on the decimal scale. Unless you're working with car stereo systems, you're not going to see a capacitor that is rated this large. We might end up working with capacitors that are the same the physical size or even larger, but that rating, that capacitor there is a 1 farad rating, which is fairly unusual overall. And it's used in car audio to ensure that there's enough juice to run the thumpy bits in the back of the trunk of typically teenage age individuals. Capacitors share similar operational characteristics to a battery. They can both be charged and discharged. The main difference is the length of time and the amount of charge that they both can store. Batteries will store charge in the form of electrochemical bonds. And so in that scenario, it's more a chemical reaction, whereas a capacitor will store charge as an electrostatic field. And so the amount of charge that a capacitor can carry is much higher, and the time that a capacitor will be able to deliver a charge will be much shorter. Let's take a look at how this is actually going to function then. So here is a capacitor. It's fully discharged. It has a voltmeter across it. It's measuring 0 volts DC. And we've got a 48 volt DC source on the left there. So we remove the voltmeter and we hook up the 48 volt DC source. And at this point, what will happen is the capacitor will charge up to the same potential as the DC source. And because of that, we're going to get some current that flows to the capacitor. So the capacitor is charging right now. Now it's fully charged. And if we were to take our voltmeter and place it across the terminals again, we would find that the voltage potential across the capacitor is equivalent to the source that it was connected to, this being a DC source. If we were to take this capacitor and then connect it to a load of a equivalent voltage rating as the charge amount that it is charged up to currently, we would get current flowing through that load. The capacitor would be discharging, and so current would flow in the same way that you would anticipate for a battery. However, it will be an extremely short time period, and that time period will really be based on the amount of resistance that the load possesses. So the capacitor, after it has completely equalized its charge, would be considered discharged. The capacitor is now discharged, and if we put our voltmeter back on it, we would see 0 volts DC. A capacitor's operation in a DC circuit will track both the voltage and the current value of the capacitor. And so we're going to look at some calculations to do with the amount of charge that a capacitor can hold, as well as calculating the values of voltage and current at different time constants in a different video presentation. For now, let's just take a look at the actual plotting of the values. So this one here, this is going to be a graph showing us the charging of a capacitor. Remember, when we're charging a capacitor, that means that the voltage across the terminals is 0. So as soon as I connect it to a source, what's going to happen? Think of it in the realm of batteries. What would happen if you took a dead battery and you hooked it up to the source? Would there be a lot of current or very little current? There'd be a lot of current, wouldn't there? There'd be a lot of current, and the voltage would slowly start to increase while the current would start to decrease. So let's take a look. Blue is the current. And so what we saw when we first hooked the capacitor up is that the current spiked to its maximum charging value. So the total current of the circuit increased substantially as soon as we connected it to the source. And that's because the source is providing current or electrons to the capacitor in order to charge it up to the same potential as the source itself. So the current spiked to a max value, and then as the potential or the voltage across the capacitor increased, the amount of current that flowed to the capacitor shrunk. And it got smaller and smaller and smaller until eventually we reached 0 amps. And the reason we have reached 0 amps is because the voltage across the capacitor is equivalent to the source. So if we look at the voltage here, it starts at 0 and then it slowly increases in an exponential curve, much the same as what we saw with current in an RL DC circuit. So this would be for charging. Let's take a look at that one more time. Remember, in an RC circuit, the time it takes for us to reach that peak value of voltage will be a correlation between the resistance of the circuit and the capacitance of the circuit. Let's take a look at discharging now. Discharging. So when we discharge a battery, what happens? The current, what happens to the current? The current starts at its max value, and then it will slowly peter off, won't it? The voltage will start at its max value and then slowly peter off. Now I've got a top and a bottom to this diagram, like an above the horizontal and below the horizontal. Down here is actually a maximum as well. And the reason that we have it sketched in this manner is because of the polarity that would be the polarity of the source and the current direction. When a capacitor is being charged, current flows into one of the terminals and out the other. But when we discharge the capacitor, the flow of electrons would be in the opposite direction, wouldn't it? As it leaves the capacitor. So that's why this graph is going to look slightly different. Let's take a look. So what's happening? They're both starting at their maximum values, and they're both decreasing down to 0. At this point here, the capacitor is considered discharged. Over here, this would have been what the voltage the capacitor was charged up to was. So perhaps 48 volts. This here is actually the exact same curve as the previous graph. It's just inverted. Don't let that scare you. It really doesn't make any difference for our calculation purposes, because really this is a decreasing exponential curve in the same way that we saw a charging capacitor. So we will take a look at some further calculations to do with this in a future presentation. And if you want to play around with some of these different simulations to do with resistive and capacitance, you can always go to the University of Colorado Physics Simulations and play them for yourself. That brings us to the end of this capacitor and capacitance presentation.